Okay. Today we have two topics. The first topic, diagonalize a matrix. This is a way to simplify a matrix. Make a square matrix into a diagonal matrix. How to diagonal a matrix? We need to use eigenvalues and eigenvectors. The second topic, diagonal a matrix can be used to solve systems of ordinary differential equations. The second topic is not required. You just listen my presentation, not required. No homework about this topic, and also the exam is not about this topic. Okay. Okay. Now, before I present these two topics, take a review about some key concepts. Review number one: whenever this equation is true, here lambda is a scalar, v is a vector, non-zero vector. Then whenever this equation is true, we say that the scalar lambda is an eigenvalue, and the vector v is an eigenvector. This eigenvector associated with the eigenvalue lambda. Review number two: whenever this equation is true, we say that matrix A and matrix B are similar. Matrix A may not be equal to matrix B, but when this equation is true, we say that these two matrices are similar. Similar matrices have many similar properties. Review number C. Whenever this equation is true, where D is a diagonal matrix. Say, for example, identity matrix is a diagonal matrix. Only the entries on the main diagonal line are non-zeros, and other entries are zeros. Then the matrix is a diagonal matrix. Whenever this equation is true, D is a diagonal matrix, then we say that matrix A is diagonalizable. We can diagonal the matrix A. Otherwise, matrix A is not diagonalizable. Okay. Then how to diagonalize a matrix? We need to use eigenvalues and eigenvectors because of the following theorem. Okay. Yeah. This is a topic one: diagonal a matrix. How to diagonal a matrix based on the following theorem. Okay, this is a theorem. Okay. If A is diagonalizable, that means that we can find matrix P, diagonal matrix D, so that this equation is true. Okay, then part A, the columns of matrix P are linearly independent. B, the columns of P are eigenvectors of the matrix A, and the diagonal entries, D is a diagonal matrix, okay? Then the entries on the main diagonal line of D, the diagonal entries of D are eigenvalues. So based on this theorem, how to diagonal a matrix A, find eigenvalues and find eigenvectors. Okay, because whenever this equation is true, the columns of P are eigenvectors and the entries of D eigenvalues. So find eigenvalues and find eigenvectors. But how to see this theorem? Okay, okay, not difficult. Say proof. There are two parts. Part A first. Okay, part A. The columns of P are linearly independent. Okay, let P column 1, I denote it column 1 by P1, column 2, P2. And here, let me suppose the matrix A, M by N. So, or the matrix P and D, M by N. P is M by N, so P has N columns, last column. Okay. Now, how to see the columns are linearly independent? Solve, by definition, solve this equation. Definition, okay, linearly independent. If this equation has only zero solution, then the vectors are linearly independent. But this equation is this matrix equation, the same, okay, same, yeah. The left side actually is P, the matrix P, times the vector X. Right. But P is invertible. P has inverse. So therefore, I can move P to the right side. How to move P to the right side? Multiply this equation by P inverse from the left. Okay, then P inverse P cancel. We get X is P inverse times 0. A matrix times 0 vector is 0. So therefore, this equation has only 0 solution. Therefore, so the columns of P are linearly independent. This is the part A of the theorem. If this equation is true, then the columns of P are linearly independent. Okay. B. The columns of P are eigenvectors, and the entries of D eigenvalues. How to see part B? Okay. Part B, proof. Part B. Okay. Start with this equation. Okay, starting with this equation, then we have the following equation. I move P inverse to the left side. How to move P inverse to the left side? Multiply the equation by P from the right side. Yeah, from the right side. From the right side. Then P inverse P is identity matrix. Or we say that P inverse and P cancel. Okay, then we have AP is PD. Okay. All right, now let me cut P into columns. All right, now let P into columns. Cut P into columns. And also cut the matrix D into columns. Okay, D, it is a diagonal matrix. That means that only the main diagonal entries are non-zero. Say non-zero, say alpha 1, alpha 2, alpha n. Then other entries all are zeros. Okay, now let me cut D into columns. The first column, alpha 1, 0, 0, 0, 0, 0. I denote the column by D1, arrow. The second column, 0, alpha 2, 0, 0, 0, 0. Denote it by D2, and so on. Dn. Then this equation, when I cut P into columns, D into columns, then this equation is A times P. Now P is P1, P2, and Pn is equal to, let me see, the right side is a P times D. Now P times D1, D2, Dn. Okay, now from this equation, recall that a matrix times a second matrix. We have two formulas to compute a matrix times a second matrix. The first formula is, one formula is A times all the columns. Two formulas. One is A times all the columns. So it is A times first column, A times second column, and A times the last column. The right side, P times all the columns. P times all the columns. All right, now compare left side and the right side, column by column. Then we have first column is equal to first column. Second column is equal to second column, and so on. The last column is equal to the last column. So we have n equations. Now take a look in detail about each of these n equations. Okay. Say for example, take a look at this equation. The first equation, take a look, for example, first equation, right? This is A. A times P1 is equal to P times D1. Okay, now let me write down the right side in detail. The right side P, matrix P, is a column 1, column 2, column N. How about D1? What is D1? D1, the first column of matrix capital D. So D1 actually is a vector. This vector. Alpha 1, 0, 0, 0, right? Okay. A matrix times a vector. By formula, we have a formula. A matrix times a vector is a linear combination of the columns of the first matrix. So it is a alpha 1 times first column, 0 times second column, 0 times third column, and so on. 0 times the last column. So therefore, this linear combination is just a scalar alpha 1 times P1. So we have A times P1 is equal to alpha 1 times P1. Whenever this equation is true, the scalar is an eigenvalue and the vector is an eigenvector. So alpha 1 is an eigenvalue, and P1, the first column of the matrix P, eigenvector, is an eigenvector. This eigenvector, of course, associated with the eigenvalue alpha 1, alpha 1. Okay, this is the first equation here. The first equation here. Similarly, second equation. Right. Right. Second equation. A P2 is equal to P times D2. Okay, now let me write P times D2 in detail. It is a P, P1, P2, Pn. How about D2? D2 means the second column of capital D. Now, second column is first entry 0, then alpha 2, then 0, 0, right? Second column of the diagonal matrix. A matrix times a vector is a linear combination of the columns of the first matrix. So 0 times P1 plus alpha 2 times P2 plus 0 times P3 and so on, 0 times Pn. But this linear combination is 0 times P1 is a 0 vector, 0 times P3 a 0 vector. So this is an alpha 2 P2. Now we have this equation. A times P2 is alpha 2 times P2. Yeah. Whenever this equation is true, alpha 2 is an eigenvalue and P2 an eigenvector. Of course, this eigenvector now this time associated with the eigenvalue alpha 2. Okay. Yeah, do the same with the remaining equations. Then we see that first equation is alpha 1 times P1. First equation. Second equation is A times P2 is alpha 2, P2, and so on. The last equation is A times Pn is equal to alpha n Pn. So therefore, the conclusion is the columns of P are eigenvectors, and the diagonal entries of A are eigenvalues. Because of this theorem, how to diagonalize a matrix A, let me make a summary. In summary, okay, how to diagonalize a matrix A? How? Step 1, find all the eigenvalues of the matrix A. Then form the diagonal matrix D, right? Put the eigenvalues in the main diagonal. Then that is matrix D. Step 2, find a P, a matrix P. Yeah, A is equal to P, D, P inverse. Matrix D is n by n. And all the columns of P linearly independent. So find n linearly independent eigenvectors. Okay, yeah. Sometimes matrix A may not have n except n linearly independent eigenvectors. In the case, matrix A is not diagonalizable. Okay, yeah, only when A has n linearly independent eigenvectors, matrix A is diagonalizable. Okay, after we find n linearly independent eigenvectors, then form matrix P. Then we get this equation. Yeah, whenever this equation is true, matrix A is diagonalizable. Okay. Let me show you examples about these 2 steps. Okay, say take a look. Okay, take a look. Okay. Example number 1. Diagonalize this matrix. 1, 3, 3, -3, -5, -3, 3, 3, 1. Okay. Okay. Let me add if possible. Okay. May not be possible. Okay. Try. Okay. Try. Okay. Okay. All right. Diagonalize this matrix. This matrix, that means that find matrix P and diagonal matrix D so that this equation is true. Okay. Now, how to find P? How to find D? 2 steps. Solution. Step 1. Find all the eigenvalues. How to find the eigenvalues of a matrix? Compute characteristic polynomial. And the zeros of the characteristic polynomial are eigenvalues. Okay, now compute characteristic polynomial A minus lambda times identity matrix. Then take determinant. Okay, determinant. Okay, then this is a matrix A. Lambda times identity matrix. So A minus lambda I is 1 minus lambda. 3, negative 3, negative 5 minus lambda. Then negative 3, 1 minus lambda. Determinant. Okay. Yeah. How to expand this determinant? Cofactor expansion. Expand the determinant across a row or down a column. Okay. Then after we expand is determinant and simplify the result, we have this polynomial. Yeah. All the zeros, all the roots of this polynomial are eigenvalues. How to find the roots? Factor this polynomial. Yeah, factor this polynomial. Yeah. So let me continue here. So the eigenvalues of matrix A are A is 3x3 matrix. A 3x3 matrix has 3 eigenvalues. Which 3? Okay, take a look. Okay, number 1, make this polynomial 0. So number 1 is an eigenvalue. Negative 2 is an eigenvalue because negative 2 make the polynomial 0. So negative 2. The third eigenvalue, take a look here. There is a power. Okay, power. So power square means lambda plus 2 times lambda plus 2. So the third eigenvalue is also negative 2. Eigenvalue negative 2 is repeated twice. We say that the eigenvalue has multiplicity 2. Okay, so okay, now eigenvalues we have found. Step 2, find eigenvectors. Okay, we have 2 distinct eigenvalues. Now find eigenvectors. Step 2. Step 2, find. Actually, we need to find 3 linearly independent eigenvectors. If we cannot find 3 linearly independent eigenvectors, then we cannot form the matrix P. Therefore, A is not diagonalizable. Okay, now we have 2 distinct, different eigenvalues. Let me find eigenvectors corresponding to eigenvalue 1 first. Okay. For the eigenvectors associated with the eigenvalue 1, eigenvalue 1. How to find eigenvectors corresponding to eigenvalue 1? Solve this equation. Yeah. Times 1 times x. Solve this equation. Okay. How to solve this equation? Move the right side to the left side. Then the right side is 0. Then factor out x. But before factor out x, let me write the second term as 1 times identity matrix. Otherwise, a matrix minus scalar 1 not computable. So let me write the second term as identity matrix times x. Now factor x up. Factor x up is 0. Coefficient matrix is a minus I. What is A? A is 1, 3, 3, negative 3, 5, 3, 3, 3, 1. This is A. Now I 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Now the difference is 1 minus 1, 3 minus 0, negative 3, negative 5 minus 1, 6, 3, 3, 1 minus 1, 0. Yeah. So this equation is A minus I, 0, 3, 3, negative 3, 6, 3, 3, 3, 0. Then times the unknown vector. This is a vector. The entries of this vector are x1, x2, and x3 is equal to 0. Yeah, this is a linear system. Now solve the linear system. How to solve it? To solve the linear system, okay, reduce the augmented matrix to the reduced epsilon form. Okay. Let me continue here. So let me erase. Continue here. Coefficient matrix. Together with right side augmented matrix. Now reduce it to epsilon form. Because I cannot use 0 as a pivot number to create zeros before, let me switch. I put the third row in the first row. Number 3. Number 3, 0. Yeah. Switch first row and the third row. Now, positive 1 times first row, add to the second row. Then 0, negative 3, 0. The third row not change. Erase. Okay. And now second, positive 1 times second row, add to the third row. Now the third row becomes 0, 0. And not in epsilon form, reduce epsilon form yet, because okay, now positive 1 perform backward elimination. Positive 1 times row 2 add to row 1, then negative 3 plus 3, 0. Negative 3 plus 0, negative 3. Yeah, here, negative 3. Now, close to reduce epsilon form. Reduce epsilon form requires the leading entries all are 1. Now, scale row 1 and row 2. Scale row 1 by dividing it by the number 3. So, divide the first row by 3. So 1. Divided by 3. So negative 1. Divide the second row by negative 3. 1. And 1. Yeah. This is reduced epsilon form. Okay, now continue. Now this time, write the reduced epsilon form in equations. Okay, in equations, first row is x1, right? x1 plus 0 times x2 minus negative 1 times x3 is 0. First equation. Now second equation is 0 times x1 plus 1 times x2 plus 1 times x3, 0. The third equation is 0 is 0. Yeah. This is the final matrix. There is a free variable. X3 is a free variable. X1, X2, basic. So the general solution, all the solutions, the general solution is x1 is equal to x3. x2 is negative x3. What is x3? x3 arbitrary. Yeah. Because an eigenvector is a vector. Write the solution in vector. Okay. Okay. Now write the solution. Okay. In vector, x1, x2, x3. What is x1? x1 is equal to the free variable x3. x3. Let me see x2. x2 is negative the free variable. Negative 3. Then x3. Now take out x3. Then we get 1. Negative 1. 1. All the eigenvectors associated with the eigenvalue 1 are this, where x3 arbitrary. So therefore, there are infinitely many eigenvectors corresponding to eigenvalue 1. Okay, eigenvalue 1. Okay, so the eigenspace associated with eigenvalue 1. What is eigenspace? All the eigenvectors together plus 0 vector. The set is eigenspace. Okay. Eigenspace is actually spanned by this vector. Spanned by this vector. So this vector is, so the set of this single vector plus 1, okay, is a basis of a space. Every space has a basis. A basis is the smallest spanning set, the smallest spanning set of the space is a basis. Because the basis has a single vector. Eigenspace, the dimension is 1. It is a one-dimensional space in R3. Yeah, each vector has 3 entries in R3. The graph is a line. Okay. But anyway, we have 1, eigenvector, and all other eigenvectors depend on this eigenvector. Okay, yeah, a scalar times this vector depend on this eigenvector. Okay. All right, now we have 1 eigenvector, independent eigenvector. But you know, the matrix P, matrix A is 3 by 3. We need 2 more eigenvectors, linearly dependent eigenvectors. Okay, now those 2, so from the second eigenvalue, okay, yeah, second eigenvalue, -2. Okay, now let me find eigenvectors corresponding to eigenvalue -2. For the eigenvectors associated with eigenvalue -2, how to find eigenvectors corresponding to -2? Now this time solve this equation. Okay. How to solve this equation? Similar to the solution above. Okay, then we get the solution. Let me skip. Okay, the solution is x2 free variable times -1, 1, 0 plus x3 times -1, 0, 1. The eigenvectors are spanned by these 2 vectors. So here, eigenspace associated with the eigenvalue -2 is eigenspace is the set of eigenvectors plus 0. It is the span of these 2 vectors. Yeah. All eigenvectors corresponding to -2 depend on these 2 vectors. So these 2 vectors, they form a basis. Okay, this is our basis. Yeah. Therefore, the eigenspace corresponding to -2 is a 2-dimensional space in R3. The graph is a plane. Okay, a plane. All right. Now we have found all the eigenvalues. Now we have 3 linearly independent eigenvectors. Okay, let me name these 3 linearly independent eigenvectors. Say, first one, V1 is this, okay? 1, -1, 1. Yeah. And the second, let me call this V2. Level 1, 1, 0. And then V3. We have 3 linearly independent eigenvectors. Now, this is step 2, find all the eigenvectors. Now, step 3, form matrix P. Okay. Step 3. Form matrix P. Matrix P, the columns are eigenvectors. Okay. Okay. Now P. We have 3 eigenvectors. Which one we should put as the first column? It doesn't matter. You can put any of the 3 vectors in the first column. Say, let me put V2 as the first column. Then V1, the second column. V3. Okay. Okay, now what is V2? Level 1, 1, 0. Level 1, 1, 0. V2. What is V1? 1, level 1, 1. 1, level 1, 1. What is V3? Level 1, 0, 1. Level 1, 0, 1. Yeah. This is the matrix P. Yeah. A is P, D, P inverse. Yeah. This is P. Now, D. Okay. Step 4. Form matrix D. Matrix D. Main diagonal entries are eigenvalues. Negative 1, negative 2, negative 2. Okay. 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 Now this time, 3 eigenvalues. Which one we should put first? Now this time, the order of the eigenvalues matters. Okay, is important. Because the first column of P is V2. V2 eigenvector corresponding to negative 2. So put negative 2 here. The order of the eigenvalues now matters. Okay, important. Okay. This is of course 0, 0 diagonal. Okay. Now, how about this entry? Corresponding to V1. V1 is an eigenvector corresponding to eigenvalue 1. So put 1 here. Don't put negative 2. Then 0. Then 0, 0. Now this entry. V3 eigenvector corresponding to negative 2. So put negative 2. This is D. Now step 5. I suggest you don't have to do step 5, but for to make sure my computation is correct, check this equation to make sure the computation is correct. Check this equation. Because this equation has inverse, I don't like to find P inverse. So let me move P inverse to the left side. Okay. Instead, okay, I check this equation. Yeah. This equation, I don't need to compute P inverse. Okay, now check. A times P. What is A? A is 1, 3, 3. Negative 3. Negative 5, 3. This is A. A. Now P. Yeah, P here. Okay. perform the product, row, column formula. Then I get 2, 1, 2. This is A times P. Now P times D. P is this is P. D, yeah, D is here. Okay, by row column formula of a matrix times a matrix, I get this. Therefore, A times P indeed equals P times D. We have this equation. So therefore, my computation above is correct. Done. So diagonalize the given matrix. Yeah, I successfully find P and D so that this equation is true. Whenever this equation is true, A is diagonalizable. Okay. All right. Second example. Now this time, in the second example, the matrix is not diagonalizable. Okay. Yeah. Example 2. Take a look. Okay. Diagonalize this matrix. If possible, okay, may not possible, okay. Solution. I want to find this equation, okay. Find this equation. Columns of P, eigenvectors. Entries of D, eigenvalues. So step 1. Find all eigenvalues. Okay. How to find all eigenvalues? Compute characteristic polynomial. Okay. It is A minus lambda times I determinant. So it is 2 minus lambda, 4, 3, -4, 6 minus lambda, 3, 1 minus lambda. Okay. Determinant. Now expand the determinant. We have negative. Okay. Lambda 2 plus 4. Factor this polynomial. Okay, so eigenvalues. Again, it is a 3x3 matrix. There are 3 eigenvalues. Okay, number one, make polynomial 0. -2 make polynomial 0. But because the power here is 2, so second -2, 3 eigenvalues. Okay. Step 1. Now step 2. We need to find 3 linearly independent eigenvectors. Okay. For eigenvalue 1. To find eigenvectors corresponding to 1, we solve this equation. 1 times x. The solution is X is X free times 1, negative 1, 1. Okay, now we have one independent eigenvector. All other eigenvectors corresponding to 1 depends on this eigenvector. Now, for eigenvalue, -2, right? -2, -2, yeah. Solve this equation. Then the solution is, let me see. The solution is X is X free times -1, 1, 0. Now this time, we only have 2 linearly independent eigenvectors. All other eigenvectors depends on these 2 guys. Okay. Since conclusion, since we only have 2 linearly independent eigenvectors. Which 2? Yeah, this one and this one. We cannot form matrix P. P is 3x3, right? 3 columns. And those 3 columns should be linearly independent. We cannot form P. Therefore, the matrix A in this example is not diagonalizable. Okay, diagonalizable. Done. Diagonalizable. Done. So a matrix may or may not be diagonalizable. Okay. Yeah. This is example 2. Now example 3. Let me pick one problem from the exercise section. Okay. Exercise section. Okay. This is one problem from exercise section. Matrix A is 5 by 5 matrix with 2 distinct eigenvalues. Say λ1, λ2. Okay, yeah. Matrix A 5 by 5 has 5 eigenvalues, but only 2 are different. Okay. The eigenspace associated with eigenvalue 1 has dimension 3. That means that corresponding to eigenvalue λ1, there are infinitely many eigenvectors, but only 3 linearly independent. Okay. All right. On the other hand, the eigenspace associated with λ2 has dimension 2. The eigenvectors corresponding to λ2 have 2 linearly independent eigenvectors. Okay. All right. Now the question is matrix A diagonalizable? Okay. And why? Okay, why? Now solution. Actually, matrix A is diagonalizable because we have 5 free from the eigenvectors corresponding to lambda 1, 2 from lambda 2. So we have 5 linearly independent eigenvectors. So we can form the matrix P. Okay. A is diagonalizable because there were 3 linearly independent eigenvectors. Say V1, V2, V3, corresponding to eigenvalue lambda 1. And there are 2 linearly independent eigenvectors. Let me say U1, U2, corresponding to lambda 2. We have 5 linearly independent eigenvectors, so we can form matrix P. P. Okay, say the order of the eigenvectors doesn't matter. Say V1, V2, V3. V3, and then put U1, U2 here. Matrix D. Now this time, the eigenvalues, the order matters. V1 eigenvector corresponding to lambda 1. Put lambda 1 here. V2 lambda also put lambda 1. Okay. Don't put lambda 2. Lambda 1. Now U eigenvector corresponding to lambda 2. So put lambda 2. Okay. Then any other entries are 0. Yeah. So this P, this D, make this equation true. So therefore, A is diagonalizable because we have sufficient number of linearly independent eigenvectors, so we can form P. All right, this is topic 1. Now, second topic. Second topic is not required, but I want to present one application of diagonalizing a matrix. Okay, yeah, solve system of ordinary differential equations. Yeah. Take a look. Okay, topic 2. Topic number 2. First, recall that if you have taken a course of differential equation, then you should know the following. Okay, recall that. Okay. This differential equation, alpha some number. Okay. One is x. Now this time x is some function. Okay. T means time. Okay. Yeah. Derivative of function x is equal to some number times x. Then solve this equation. That means that find out all the function x. The solution is x is equal to c. C can be any number. E to alpha t. Yeah, these are all the solutions. Where C is an arbitrary number. or scalar, okay, scalar, arbitrary number. How to see this guy is solution of this equation? Plug in this guy in X. That means that take derivative on this guy by chain rule, okay, chain rule. Then plug in this guy on the right side. Then you will see, yes, left side is equal to the right side. This is solution. Okay, solution. Okay. Now, based on this result, take a look at the following example. Okay. Example 1. Suppose a particle is moving in a planar force field, okay, and the particle's position, let me denote it by vector. X coordinate is x1, x2, right? Let me draw a diagram. Yeah, this is a x1, x2. The particle is moving in a planar force field. Say moving, yeah, moving, yeah, yeah. The position is this point is x1, x2. Of course, because the particle is moving, the position depends on the time t. So x1, x2 are functions of the time t. Okay. Suppose a particle is moving on the plane and its position satisfies this system of ordinary differential equation. X1 derivative is equal to 4x1 minus 5x2. Then derivative of x2 is equal to negative 2x1 and x2. Okay. Yeah. Okay. Initially, when time is 0, okay, initially, we know the position of the particle. Okay. X1 coordinate is when time is 0, it is 2.9. X2 is 2.6. That means that this point, the location is 2.9, 2.6. Okay. Now the question is find the position of the particle. Find the function x, find x1, find x2. Then how to solve this problem? Okay, how to solve this problem? If the differential equation is a single vector, we have solution. Now, not single vector. How to solve it? Use matrix, diagonalize matrix. Okay. Okay. Now solution is solution. We first write the differential equation system. Okay. Yeah. This system. Let me give a name to this system. Okay. 1. The system 1 into matrix equation. Okay. So let the right hand side coefficient, take out the coefficient. Okay. Then left side is 4, negative 5, negative 2, 1. Then the system of differential equation is left side is derivative on the vector x. Right side is a times the unknown x, unknown vector. Yeah. The right side is matrix A times the vector x1, x2. Left side derivative on the vector x1, x2. Yeah. All right. Now, diagonal lies the matrix A. Okay. Now, matrix A is P D P inverse. Now P -5 1 2 1. D diagonal 6 0 0 -1. And then P inverse. I don't compute P inverse. So P then inverse. Hey, then this equation is dx dt p d p inverse then times x, right? Because matrix A is this, so I plug in this in A. Okay. Now from here, I move P to the left hand side. Okay. D P. Okay. Because P a constant matrix, I can move it inside derivative. D times P inverse. Okay, now below this by 1. Below this by 1. Then we have derivative on y. dt is d. D. Diagonal matrix times y. In details, it is what is that? It is because 6 times y1 plus 0 times y2, so 6 y1. This is 0 times y1 plus -1 times y2. So therefore, we have right side compare the first entry. Compare the second entry, y2, negative y2. Yeah. So we have a system of 2 single differential equations. Now, the solution of the first is y1 is arbitrary constant times E6t. Second equation is y2 is arbitrary constant times e to negative t. Yeah. So we get y. After we get y, we get x because P inverse x is y. So move back P to the right side. After we get y, then we get x. After we get x, we get the moving position of the particle. How to determine C1, C2? We have initial condition. We use initial condition. We can tell C1 and C2. Yeah. For the details, you can take a look at my notes, but this topic is not required. Yeah, let me stop here today.